In this video presentation, a flexible method is shown for adding reliable standard trace concentrations of vapours into small to medium gas flows. With the following two slides, I shall explain what we mean by a vapour and how a vapour differs from a gas. An ideal gas has all its molecules moving around separately. Ideal gases obey Boyle's law about the inverse relationship between the gas pressure and the volume of a given amount of gas at a constant temperature, and Charles's law about the direct positive relationship between the volume of a given amount of gas and its temperature at a fixed pressure. In contrast, a vapour differs from an ideal gas because the molecules are often associated in clusters of two or more molecules. It is a non-ideal gas below its critical temperature. So, a vapour can be liquefied or solidified. Liquids can evaporate to form vapours. Solids can also sublime to form vapours directly without melting. What are trace vapour concentration standards? Often we have to generate a very small or trace concentration of a vapour in a flow of gas. Frequently, we need to control reliably the very small concentration of that trace vapour, repeatably and reproducibly in the diluting gas flow. When we do that, we are then making trace vapour concentration standards. We can use such trace vapour concentration standards for many purposes. One common and important example is in calibrating chemical analyses by instruments such as mass spectrometers, gas chromatographs, or a combination of the latter two, namely gas chromatograph mass spectrometers, GC-MS. There are many ways of making trace vapour concentration standards, including static standards, for example, gravimetric standards in compressed gas cylinders. For many reasons not dealt with here, it is very much better to use dynamic standards, upon which this presentation is focused. And examples of ways in which these are prepared include using syringe drivers, permeation tubes, and diffusion tubes. In this video presentation, I'd like to focus on the latter two. Permeation tubes are a very popular means by which we can simply generate a standard rate of emission of a vapour under thermostatically controlled conditions. If such permeation tubes are placed in a well-controlled gas flow, then we can dynamically generate standard concentrations. These devices are made conventionally from PTFE tubing, filled with the VOC or SVOC of interest, and sealed at each end with solid PTFE plugs, as shown in the photograph. Thermoplastic polymer tubing, such as PTFE, is readily permeable to the VOC or SVOC molecules through its amorphous structures, and if this permeation occurs at a thermostatically controlled temperature, the permeation rate will be constant. Permeation tubes are calibrated gravimetrically by regularly weighing the thermostated device over a period of time, which can often be weeks or months. Up to 3 to 6 months is not uncommon. This enables us to estimate the rate of weight loss, which is equivalent to the permeation rate. As such tubes are usually not refillable devices, once the VOC or SVOC filling has been exhausted, that tube is not reusable. The cost of calibration and safe filling of commercially available tubes can be considerable. Also, the number of commercially available types of tubes and of compounds is limited. But there is now an alternative and much more flexible way of making such standards without such expense or other limitations. The Tracer Cert diffusion tubes from Tracer Measurement Systems Limited can be used with volatile or semi-volatile compounds, both organic and inorganic, in thermostatically controlled ovens, such as those made and marketed by our distributor Eco Scientific Limited, whose contact details are given at the end of this PowerPoint video. The tubes are designed to allow the rate of diffusion of vapour out of the tube to be carefully controlled in specific ways. When used at a set temperature in such an oven, the vapour of the compound is emitted at a steady rate, which is determined by the properties of that compound, by the set temperature, and by the particular dimensions of the diffusion tube used. The higher the temperature used, the greater the rate of diffusion of vapour out of the tube. The vapour diffuses out into a flow of carrier gas. The larger the gas flow used, the greater the dilution of the vapour, and the smaller will be the concentration obtained. The tube is made with a specific length of precision bore glass tubing of a specific internal diameter or bore, which is attached to a 2-compartment glass reservoir with a screw thread and cap for sealing. A wide range of nominal internal diameters is offered for these tubes, ranging from 0.1 mm to 4 mm. Diffusion tubes are available with nominal lengths of the precision bore tubing between 2 and 10 cm in steps of 2 cm. Permeation tubes can only be used once because they are usually not refillable once the contents have been exhausted. By contrast, Tracer Cert diffusion tubes are refillable and reusable more or less indefinitely with the same substance, and so are much more cost-effective than permeation tubes. These robust devices are usable up to 180 degrees C, so they can be used with both liquid and even solid VOCs, SVOCs, and in organic substances such as water, bromine, or iodine, even with low or very low vapour pressures. Sometimes, instead of directly using a compound to generate its vapour, we can use a compound that, when heated, decomposes to the vapour of interest. For example, metaldehyde, which decomposes to the original monomer acetaldehyde, or the polymer paraformaldehyde, which decomposes to formaldehyde when heated in a dry gas flow. Each tube is uniquely identifiable with an easily readable, laser-engraved, individually assigned code, making them very useful in audit trails and quality assurance schemes. Tracer Measurement Systems Limited has a record of every tube made and sold. Neither Tracer nor Eco Scientific will deal with inquiries about tubes which are not genuine Tracer Cert diffusion tubes. Such copies are likely to be very inferior attempts at making our high-quality precision products. What do we need to know or to be able to estimate to help us to choose suitable tubes for our requirements? The smaller the bore and the greater the length of the precision bore part of the diffusion tube, the smaller is the rate of diffusion of vapour out of the tube. Vapour concentrations can be generated over a wide range, from below ppb to very high ppm. So when trying to choose a suitable tube, we need to know what range of concentrations of the vapour is needed. It is best to use concentration units that are reliably calculated or estimated, and not subject to the confusion often found with ppm, ppb, etc. Examples of best practice would be nanograms or picograms per litre, nanomoles or picomoles per litre, and so on. We need to know the molecular weight of the volatile substance, and preferably also its diffusion coefficient, and vapour pressure, and how they vary with temperature. Using those, we can then estimate the diffusion rate of the vapour out of the tube at particular set temperatures in nanograms or nanomoles per minute or per second, for example. If we don't know either the diffusion coefficient or its variation with temperature, our instruction leaflet explains how to estimate those properties. Similarly, if we only know the melting and boiling points and just one vapour pressure between those temperatures, the leaflet explains how to estimate the vapour pressure at any particular temperature. The first step in using Tracer Cert diffusion tubes is to remove the red screw cap and pipette a small volume of the volatile liquid into the reservoir. Alternatively, with a solid, use a semi-micro spatula to place a small amount of powder or crystals into the reservoir. After that, replace the screw cap and tightly screw it back onto the tube to seal that end, and weigh the tube using a precision balance able to weigh to plus or minus 0.1 milligram, or for example using the semi-micro precision balance with which we can weigh up to plus or minus 10 micrograms. After weighing the tube, carefully place into the thermostat oven at the desired temperature with a piece of fine wire wrapped around the narrow neck between the two sections of the reservoir. This is a very simple way of enabling the user to pull the tube out with tweezers when taking it out for the regular weighings during calibration, as well as when you want to refill it. In the right-hand photograph, with the diffusion tube placed in thermostat oven glass compartment and its sealing cap back in position, you will see two plastic tubes through the sealing cap. One goes right to the other end of the glass compartment and is for the input of the carrier gas, and the other is for the output of carrier gas, now with the added trace vapour. The latter output tube can be connected to whatever device the user may wish to calibrate. The carrier gas could be zero air, purified clean air, or, when working with oxygen-sensitive compounds, oxygen-free nitrogen, for example. Care should be taken to allow the diffusion to adequately equilibrate at the set temperature before starting the regular weighings for the weight loss estimation for calibration. Periodically weigh the tube over a period of hours, days or weeks in order to collect sufficient weight loss data versus time to estimate reasonably well the diffusion rate of the vapour out of the tube using linear regression analysis. If you would prefer, via our distributor EcoScientific, you can have the diffusion tubes which you purchase calibrated for a standard fee per tube by Tracer Measurement Systems Limited. Tracer Cert diffusion tubes and suitable ovens in which they may be used can be obtained from our distributor EcoScientific Limited, whose contact details are shown on this final slide. I hope you have found this presentation helpful, and we look forward to receiving your orders for our diffusion tubes. Thank you for listening.